Okay, let's move on. We have discussed the ferrocene in the last class, which was the first metallocene that has been discovered. And as I said, this has triggered a lot of follow-up research because of the intriguing bonding within the ferrocene, and soon after the discovery of the ferrocene, scientists started to look at, well, what other metallocenes are possible. Okay, so one question was, of course, is the metallocene chemistry restricted to cyclopentadiene chemistry with a cyclopentadienyl ligand, or can also other cyclic pi ligands be used to produce metallocenes? So probably the most basic cyclic molecule with conjugated pi electrons is the benzene. So one question was, can benzene also act as a hexahaptoligand using all of its 6 carbon atoms and the 6 pi electrons to make a metallocene? So we can think about which metallocene we would expect to be most stable. So we have previously seen that the 18 electron rule is being fulfilled for the ferrocene. So we can think about what metal would we actually need to combine with benzene as a ligand to fulfill the 18 electron rule as well. And that metal would then most likely make a stable metallocene with benzene as a ligand. So what do you think? Which metal would you choose to combine with benzene to form a metallocene, assuming that the 18 electron rule holds? Can anybody provide an answer to this? Nobody knows an answer? Okay, then I will give the answer. So let us do the electron counting. Okay, so well, first of all, here's the answer. So it's actually the chromium that would most likely make a stable metallocene compound, and indeed the bis-benzene chromium is also known. Note that chromium here is actually in the oxidation state 0, because we would consider the benzene as a neutral ligand, whereas we would consider the cyclopentadienyl as an anionic ligand. All right, so now the 18 electron rule is fulfilled if we use chromium, because chromium is a group 6 metal, has 6 electrons. So the oxidation state is actually 0 and not +2. So this is again a mistake here on the slide. Apologize for that. But here the number of electrons is correct. It's 0 electrons that we add or subtract. Then the ligands contribute 6 electrons each. We have 2 ligands, so that gives 12 electrons, and we overall get 18 electrons. So now we can not only make the ring larger than a 5-membered ring, like we've done just now. We can also look at rings that are smaller. So for instance, we can ask, can we also use cyclobutadiene as the ligand. In this case, the cyclobutadiene would be a tetrahaptoligand because it would use all 4 carbon atoms and its 4 pi electrons in order to make the metallocene. So there is a difference in the cyclobutadiene ligand in comparison to the cyclopentadienyl and the benzene ligand. So in the previous ligands, we had both 6 pi electrons, and therefore our ligands were aromatic ligands according to the 4n plus 2 rule, okay, whereby n is just an integer number. So when n is equal to 1, then 4n plus 2 is equal to 6. So a cyclic 6 electron pi system is therefore an aromatic system. So this is not the case for cyclobutadiene, where we only have 4n electrons. And conjugated pi system that has 4n electrons is called an anti-aromatic system. And anti-aromatic systems have less stability than aromatic systems. So this is the reason why cyclobutadiene is actually not stable in the free form, but it can actually be stabilized by being a ligand attached to a transition metal. So let us understand why the cyclobutadiene is not as stable. So there's certainly the ring strain in this 4-membered ring, but in addition to that, not all electrons are in bonding molecular orbitals, and that results in the anti-aromaticity. So you see here the 4 molecular orbitals of the pi system. So one is bonding, and you see that the respective molecular orbital doesn't have a node. Then we have these 2 anti-bonding molecular orbitals that have 1 node. You see in the first one, we switch from a negative to a positive algebraic sign here, whereas in this molecular orbital, we switch from a positive to a negative algebraic sign over here. Okay, so the nodes are in 2 different positions, but we can easily see that both electrons are equivalent degenerate because they are just rotated by 90 degrees relative to each other. Okay, so last but not least, we have this anti-bonding molecular orbital here, which has 2 nodes. You see the first node here, and you see the second node here. So on the neutral cyclopentadiene molecule, we have 4 electrons. So we can now fill the bonding molecular orbital, but in addition, we must fill the 2 non-bonding molecular orbitals, and you see now you do not have ideal bonding situation anymore because you must accommodate 2 electrons in non-bonding molecular orbitals. Okay, so now let us look closer at the shape of the cyclobutadiene. So here in this diagram, it is kind of implied that the cyclobutadiene would be square planar, but it's actually not square planar, it's rectangular. So we have here an effect, which is called the Piles distortion, which is the same as a Jahn-Teller distortion. So we saw previously that Jahn-Teller distortion occurs when we have partially filled degenerate orbitals. Then we have a driving force for the molecule to distort. We saw this in an octahedral D9 complex, and the same effect can also happen in simple organic molecules. The cyclobutadiene is one example. So if the cyclobutadiene was a square, then we would assume that all the pi electrons are completely delocalized. Okay, And well, we could justify this by the fact that, well, we have the possibility to localize the pi electrons either between these two carbons and these two carbons, or we locate them between these two carbons or these two carbons. And therefore, we can draw two resonance structures which are equivalent, and according to what we know about resonance, we would expect, well, the real electronic situations in between in our pi electrons are actually delocalized, and therefore our molecule would expect it to be square. However, this isn't correct. The pi electrons are not delocalized, they're actually localized, and that leads to the distortion. And we can explain this distortion, the Jahn-Teller distortion, quite easily when we consider what happens to the energy of the pi molecular orbitals due to the distortion. Okay, now you see here again the non-bonding pi molecular orbitals, and you see again that this molecular orbital is rotated by 90 degrees relative to this molecular orbital. Okay, according to Hund's rule, we would fill both electrons spin up into the two different orbitals. So this would relate to the square structure. Now let's see what happens as we distort. So there are basically two ways to distort. So the first way is that we make these two bonds longer and make these two bonds single bonds, and these two bonds become double bonds. Okay, then this structure seen here would result. So now what will happen to the energies of these two orbitals as the structure distorts? So you see that as we bring these two carbon atoms and these two closer together and these two further apart, that this weakens the bonding interaction between these two p orbitals and also weakens the bonding interactions between these two p orbitals. Okay, but it increases the interbonding interactions between these two and these two. So therefore, our orbital will now be overall interbonding, and it will move up in energy accordingly. So now, what about this molecular orbital here? Well, to this molecular orbital, the opposite happens. So as we bring these two carbon atoms closer together, these bonding interactions here strengthen. As we bring these two carbon atoms closer together, the bonding interactions between these two orbitals increase as well. And the interbonding interactions between these two orbitals here, they decrease, and the same happens to the interbonding interactions between these two orbitals. So that means that overall, our orbital has become somewhat bonding, and the energy decreases. So now what can we do with these two electrons? Well, we can fill them into the two bonding molecular orbitals by pairing their spins, and therefore we have achieved a net stabilization of the electron, which explains our distortion. Okay, now we could say, well, we can also distort a different way. We make these two bonds shorter here and localize the double bonds here and here, and make these two bonds longer and realize the single bond here and here. So what would happen to the orbitals then? Well, in this case, this non-bonding molecular orbital here would become bonding, and this blue non-bonding molecular orbital would be interbonding. Okay, so now you see that these two are the two resonance structures that we could draw, but you see that these two molecules are actually identical because we can make the two superimpose by rotating one of them just by 90 degrees. Okay. Therefore, both distortions are actually equivalent, and we only would need to consider one in order to explain the change in the electronic situation, the distortion satisfactorily. So now we understand why our cyclobutadiene molecule is not square planar, but it's actually rectangular. So now how does this molecule behave as a hepta-4 ligand? Can we actually make metallocenes with this ligand? So in order to fulfill the 18 electron rule, which metal would you combine with two cyclobutadiene molecules to make a metallocene? When you look at the fourth period of the periodic table. So we said for the benzene we need the chromium. So now for the cyclobutadiene, which metal would you use? Nobody has an idea? Okay, well, let's just count the electrons again. So each ligand would have 4 pi electrons. We have 2 ligands, so that means that we have 8 pi electrons. So the metal would need to have 10 electrons. That would give 18 electrons. So which metal in the fourth period has 10 electrons? Well, it is the nickel. So now, do we know such a compound? The answer is not quite. But derivatives of the nickel dicyclobutadiene is known, in particular the derivative with 4 phenyl substituents at each cyclobutadiene unit. Now, interestingly, in this compound, the cyclobutadiene is not distorted anymore, but it's actually really square planar. So real square. And of course, you can now ask what explains this behavior. And an oversimplified explanation is that, well, we can call the cyclobutadienyl ligand an aromatic ligand if we treat it an anionic ligand, in which the cyclobutadiene unit is 2 additional electrons that are in the non-bonding orbitals. And the non-bonding orbitals are being full, and there's no driving force for the distortion anymore. So in this case, the nickel would be in the oxidation state 4+. However, this would be an unusual oxidation state for the nickel. Therefore, we should consider this explanation as an oversimplified explanation. We could even do the opposite and say, well, if you remove 2 electrons from the cyclobutadienyl ligand, then we have also an aromatic system of 2 electrons. But in this case, then our nickel would be on the oxidation state 4-, which would be kind of unusual as well. So there are other examples in which cyclobutadiene acts as a ligand, and whenever it does, it actually makes a square. So here's another example in which one cyclobutadiene molecule is attached to this iron tricarbonyl unit here. And again, an oversimplified explanation would be that the cyclobutadiene can be considered as an anion, and then the oxidation state of the iron would be assumed to be 2 plus. All right. So yeah, here's just the image that supports what I just said. When we fill here 2 electrons into these non-bonding orbits, we have 6 electrons, and then our ligand is formally aromatic, and the driving force for distortion goes away. Okay. Now, what about even larger ligands? What about the cyclooctatetraene as a ligand? Also, here we have a cyclic ligand with conjugated double bonds, in this case 4 conjugated double bonds. How does this ligand behave? So first of all, we again need to realize that this is an anti-aromatic ligand. So we have again 4 n electrons. In this case, n is equal to 2, and we have 8 electrons. So can we use all the 8 electrons to make a metallocene? The answer is yes, but only under certain circumstances, in particular when our metal is a very large metal. So that is, for instance, the case for the uranium, and indeed the uranium makes a uranosine with cyclobutadiene. Interestingly, then again, not with cyclobutadiene, but with cyclooctatetraene. So interestingly, in this case, the cyclooctatetraene is planar again, and again, an oversimplified explanation would be that we treat the ligand formally as a 2- ligand, then we have 2 more electrons in each ligand, and then we have formally an aromatic ligand. So in this case, and in this view, the uranium would be then a uranium 4 plus. Okay. Now, in addition to that, the cyclooctatetraene can bind in different ways. So it cannot only be a octa haptoligand, but also a hepta-2, a hepta-4, and a hepta-6 ligand. And these binding modes are then realized when we have smaller metal ions. So complexes with these metal ions then mostly obey the 18 electron rule. So just a few examples. So here this ruthenium complex is known, where you have this ruthenium tricarbonyl unit that binds to the to 2 double bonds here in the cyclooctatetraene unit. And if we counted the electrons, we would find that we have 18 electrons. We can just do this. So the ruthenium has 8 electrons. Then these carbonyl ligands contribute 2 each. So we have 8, 10, 12, 14. And now we have these 4 pi electrons in addition, which gives 18. So this explains why this ligand binds in a hepta-4 mode and a hepta-2 and hepta-6, just uses the number of pi electrons to achieve 18 electrons. So here is just another example where 2 ruthenium tricarbonyl units bind to the cyclooctatetraene unit. So in this case, contrast to here, also the other 2 double bonds are being used to bind to another ruthenium tricarbonyl unit. But again, of course, for each ruthenium, we would have 18 valence electrons. All right. Then this is what I wanted to say about Metallocenes. We can now move over to the next chapter and discuss another interesting class of organometallic compounds, which is the carbonyls. So we have looked at the carbonyl ligand order quite extensively. Now let us look more quantitatively at what carbonyls metals make. So basically, carbonyl complexes are complexes between carbon monoxide and metals. And why are they interesting? They have a great structural diversity. Okay, so diverse coordination chemistry. So in addition to that, they have a lot of synthetic use. They are frequently used as starting materials for other coordination compounds. That is because the ligand, the carbon monoxide, is a gas, so can easily drive a substitution reaction by Le Chatelier's principle. You remove the carbon monoxide, which is the leaving ligand, from the chemical equilibrium, and then that drives the chemical equilibrium to the right side. So the CO ligand can also be replaced in a facile way by other ligands, partly because of the argument that I stated. One can drive it pretty easily out of the reaction system, but also the carbon metal bond is, well, not too unstable, but it's also not too stable. So these carbonyls often have a moderate stability, and the metal ligand bond is moderately stable enough so that your starting compound is not too unstable and not too difficult to handle. But still, the metal ligand bond cleaves easily enough so that you don't need drastic conditions in order to make the substitution reaction happen. So a further argument is that the CO unit is a C1 unit, and again, you can do a lot of synthetic chemistry with this. So carbonyls have a lot of applications in catalysis for organic synthesis, and you can insert C1 units into other organic compound using carbonyls as catalyst intermediates. And last but not least, more interesting from a fundamental standpoint, carbonyls stabilize low oxidation number of metals. So typically we associate metals with positive oxidation states. We are very familiar with metal cations. We are not so familiar with metals in negative oxidation states, and we will see that carbonyls do stabilize metals even in highly negative oxidation states, and we will learn why that actually is. So now let us first look at why the coordination chemistry of carbonyls is actually quite diverse. This becomes clear when we look at the molecular diagram of the carbon monoxide, again in somewhat more detail. So we have discussed that here this 3A1 molecular orbital is an epoxy non-bonding molecular orbital, which is the HOMO, and this molecular orbital here in the molecular orbital picture represents approximately this electron pair at the carbon. This molecular orbital here is also located primarily at the carbon, and that explains why the carbon is actually the reactive end. So in one binding mode, the carbon monoxide can just use this electron pair here at the carbon atom to bind two transition metals. But in addition to that, we have here these pi bonding molecular orbitals that are energetically not too low, and they can be involved in the bonding as well. Then we have here these anti-bonding pi star molecular orbitals, which are energetically not too high and can be used for bonding as well. In particular, the carbon monoxide ligand, as we said before, is actually known as a quite strong pi accepting ligand, and that's because of these relatively low lying pi star anti-bonding orbitals. Last but not least, it is even possible to use this molecular orbital here in the bonding. So this molecular orbital here is also approximately non-bonding and represents the electron pair of the oxygen. But you see that the energy of this molecular orbital is lower than the energy of the pi orbitals and the energy of the HOMO. Therefore, we find that this molecular orbital and this electron lone pair is rarely involved in the bonding, but under certain circumstances, it can even be involved in the bonding as well. So now, to which structural possibilities does this translate? So first of all, let's look at the sigma binding modes of the carbonyl ligand. In the most simple case, the carbonyl ligand uses its electron pair here at the carbon and donates 2 electrons into a single metal. Okay, then we say that the carbonyl is a terminal binding mode. However, it cannot only donate this electron pair only into one metal. This electron lone pair can also be shared between 2 metals that are interconnected by a metal-metal bond, and not only 2 metals are possible, it can even be shared between 3 metal atoms. So in this case here, we say that we have a mu bridging carbonyl ligand, and in this case here, we say we have a mu3 bridging carbonyl ligand because 3 metals are being involved in the bonding. So last but not least, we can also have a so-called semi-bridged binding mode. That typically occurs when we have 2 different metals that are interconnected via a metal-metal bond. And it's often the case that the electron lone pair here interacts more strongly with one metal compared to the other. So the bond lengths are therefore then unequal and the interactions are unequally strong. We call this a semi-bridging carbonyl ligand. So in all these cases, the carbon monoxide acts as a 2-electron donor. So what else is possible? Well, it is also possible that the pi electrons are used for sigma bonding. Okay. However, the pi electrons can only be used after the electron lone pair here has already been used, and that is because this electron lone pair has a higher energy than the pi electrons here. Okay, but because of that, it is possible that when we have a long metal-metal bond, that But what the electron lone pair here at the carbon is being used to make a regular single bond with the metal, but then the pi electrons here in the carbon oxygen one overlap in a sigma fashion with the metal d orbital to make additional sigma interactions. So in this case, our carbonyl ligand is a mu2 hepta2 4 electron donor. Mu2 because it is bridging, and hepta2 because now both the carbon and the oxygen are being involved in the bonding. The oxygen involved in the bonding because part of the electron density in the pi orbitals is located at the oxygen. So now these pi electrons can even be donated into two different metals. That is possible because, well, we have two pi bonds available that stand perpendicular to each other, and one pi bond can be used in order to make sigma interactions with the first metal, and the second pi bond can be used to make sigma interactions with the second metal for energetic arguments. Again, this is only possible after the electron pair here at the lone pair at the carbon has already been used to make interactions with another metal. So in this case, we have a mu3 hepta2 6 electron donor. It is mu3 because now we have 3 metal atoms involved. It's again hepta2 because both the carbon and the oxygen are involved in the bonding with the metals. And we have a 6 electron donor because now, in addition to the electron pair of the carbon, also 4 pi electrons in the ligand are being donated to metals. Okay, then there's even a third possibility, which is that the electron lone pair at the carbon is being shared between two metals. Okay, and then one pi bond is being used to interact with the third metal in a sigma binding mode. And in this case, we have then mu3 hepta2 4 electron donor. Again, mu3 because 3 metals are involved, hepta2 because both the carbon and the oxygen of the ligand are involved. And you have a 4 electron donor because the electron lone pair at the carbon makes interactions, and 2 pi electrons in the ligand make additional interactions. Okay, last but not least, it is also possible under certain circumstances that we have a so-called isocarbonyl, in which the electron lone pair at the carbon is being used, and the electron pair at the oxygen is being used, but not the pi electrons. That is possible under certain steric conditions. So in this binding mode, again, the carbon monoxide acts as a 4 electron donor because the electron lone pair at the carbon as well as the electron lone pair at the oxygen is involved in the bonding. But this case here is relatively rare because, or fairly rare actually, because the low-lying electron lone pair here of the oxygen, which does not easily interact with another metal. Okay, now what about the pi bonding modes for the carbonyl ligand? So there are two ways the pi orbitals can be involved. So first of all, carbon monoxide is a typical pi acceptor. So therefore, it favors to use pi star orbitals over its pi orbitals when making interactions with the metal. You see here how pi interactions based on end-on binding can occur. So these pi interactions can happen in addition to the sigma interactions between this carbon here and the metal here, as the carbon monoxide ligand binds end-on to the metal. So you see here the lobes of one pi star orbital of the metal, and you see that we can easily make pi interactions between the two large lobes that are located at the more electropositive carbon. And therefore, these pi interactions create a significant overlap, and then for these pi interactions can actually be quite strong. So in addition to this, there's also the possibility that metal binds side-on to the carbonyl ligand and makes interactions between two lobes of the d orbitals and two lobes of the pi star orbit. So these interactions are not quite as effective as the end-on interactions because of the uneven size of the two lobes of the pi star orbital here. So we would expect that the interactions between this lobe and that lobe may be significant, but the interactions here would expect to be significantly weaker. Therefore, the overall interactions are significantly weaker in comparison to the end-on binding as a general rule. Okay, now it is important to note that there are synergistic interactions between the sigma donor and the pi acceptor interactions as the carbonyl ligand binds end-on to a metal. And that is called the Dewar-Chet-Duncanson model for carbonyls. So this works the following way. We have here our carbonyl ligand that wants to bind end-on to the metal. So it can create a sigma bond by sigma donation of its electron lone pair into the metal orbital. But now, this process increases the electron density on the metal. So therefore, the metal has an increased desire to, return some of the electron density to the carbonyl ligand, because now our metal is actually formally negatively charged. So now it can do this through the pi acceptor interactions. Okay, by interaction of a metal d orbital, which is full, with the empty pi star orbital of the ligand. Okay, and that can create an additional metal carbon bond, which, however, is dative in the opposite direction. So electron density is donated from the metal to the ligand, and then as electron densities fill into the pi star orbitals of the ligand, the bond order within the carbonyl ligand is being reduced. Okay, as shown here. Yeah. This fashion, just switches back and forth. Okay, so now the net effect is that we have increased the bond order between the metal and the carbon, and that means that we have increased the strength of the metal carbon bond, and that leads to the stabilization of the carbonyl molecule as a whole. Okay, therefore, the pi acceptor interactions are very important for the stability of a carbonyl. The better we can realize these pi acceptor interactions, the more stable we would expect our carbonyl to be. Okay, so let's look more closely at this. We can, in principle, distinguish between three cases. So in the first case, we say, well, our pi acceptor acceptance are fairly weak, even though they can happen, and we can neglect them. And then we would write our metal carbon bond as a single bond and our carbon oxygen bond as a triple bond. So now we can assume, well, we have significant pi acceptor interactions. And in this case, like here, we would say we have a metal carbon double bond and a carbon oxygen double bond. But we can even use a second pi star orbital here for additional pi acceptor interactions. And then we would have even a metal carbon triple bond and only a carbon oxygen single bond. And this would relate to very strong pi acceptor interactions. So now you may ask, well, under which conditions are these three cases being realized? And the answer is it depends on a lot on the charge of the carbonyl. So when we have carbonyl cations, in particular when the charge of the carbonyl cation is larger than 1, then this case is being realized. Okay, that is because when, well, we have a cation, then we have formally the metal on a positive oxidation state. There are relatively few, the electron density on the metal is relatively small, and therefore the tendency of the metal to pi donate electrons into the pi star orbitals of the carbonyl is fairly small. So when we have weakly charged carbonyls, -1, 0, +1, then most often this structure describes the bonding situation in these carbonyls correctly. So the electron density, the charge density on the metal increases, therefore the tendency of the metal to pi donate electrons into the pi star orbitals of the ligand increases. So now when we have carbonyl anions that have a charge larger than -1, then we have even more electron density on the metal. And therefore we have even more tendency of the metal to back donate electron density to the pi star orbitals, creating then a metal carbon triple bond and a carbon oxygen single bond. Okay, let us stop at this point and then look in more details at what carbonyls actually being realized in nature in the next class. So I'm just stopping the recording here, but there will still be time to answer questions.